So welcome back guys, this is Madhav PVL and today we are going to discuss completely about the kernel in the Unix operating system, and we are also going to discuss about the file distribution and file systems in this Unix operating system. So before getting into that, so introduction to the kernel architecture of a Unix system. So I need to just show you one image. So this is a basic architecture of a Unix operating system, user level, kernel level, hardware level. So these are the three levels which we can just see in this operating system. So if we just start here, user programs. So user will just access the program with the help of some system call, or either he will just mention the libraries and then he will just explain his problem and he will just seek for the solution. So here we have two scenarios like so the user program is directly calling the system call. Now let us just consider the situation of calling direct system call. So if a user calls a system call directly, then it will just search in the library and then again it will just bring back that system call details which are regarding that from that library, and it will just get into this file subsystem, and in this file subsystem it will just get into this buffer cache, and in the buffer cache it will just get to this device drivers. So from the device drivers it will just bring the required drivers which were required for this particular process to be completed, and if the system thinks that these drivers are required for the further purpose, then they will just put those things in this buffer cache. So buffer cache will just consist of some files, not the every file, not the every driver. So only some drivers which were repeatedly used by the user with the help of this file subsystem will be stored in this buffer cache. So for the further usage they will just store them in this buffer cache. And then again if we just come back to the system call interface, so from system call interface the system call will just get into this process control subsystem, and in this process control subsystems here we can just see the inter-process communication, scheduler, memory management. So here the kernel plays a major role. Here if we just come here, so the kernel will have different n number of processes. So here we need to just execute one more new process, right? So for executing this one more new process there should be some inter-process communication. So one process requirements may be important for the another process requirement. So inter-process communication should be done, and then scheduler is nothing but not so many processes running at a time. It will be so much stressful for the kernel, so it will just run one after the another. So it will just schedule the processes one after another, and then memory management is nothing but the way they will just store the things which were required for the process, the data given by the user, or the inode values or the other things, inode values or the file tables or the file descriptors, the whole things, the both input and the output, whole thing will be stored in this memory management. And then finally if we just get into this hardware control, finally it will just gain some hardware control along with the device drivers and also with the process control subsystems, along with these all three functionalities it will just get back to this hardware control, and from hardware control it will just give the output to the user with the help of this hardware. So hardware level is nothing but giving some output to the user. So this is the basic understanding of this architecture of a Unix operating system. So again we will just get back to the content. So now here we can just see, one second guys. So here we can just see the file subsystems. So the main aim of the file subsystems is to manage files and allocate file space, administer free space, and then control access for the users. So the buffer mechanism is to interact with the IO device drivers. So the most used device drivers will be stored in this buffer cache memory. So they will be just stored in this cache memory. So the buffer mechanism to interact with the IO device drivers. So one by one package by one package, they will just bring the data regarding this device drivers to this buffer. So the device drivers are the kernel modules that control the operation of a peripheral devices. To complete a particular process, it requires different number of device drivers. Different number of device drivers are nothing but the different number of peripheral devices. So to complete a process we require more than 2 to 3 number of devices, right? So for this all devices we need some device drivers. So all these device drivers are the kernel modules that control the operation of a peripheral devices. So here we have two types of subsystems. They are process control subsystem and then hardware control subsystem. Process control subsystem is nothing but the process synchronization, whereas bringing back the data at every instance, bringing the data or bringing the status of a particular process, status of every process, synchronizing every status of a process at a particular time. Inter-process communication, as I had said before, communication between different number of processor. For if here we can just consider one example. If a person one travels till one place, and then if he just finds some problem at that particular place, he will just upload it in the Google map saying that here it is an interrupt. So it will just show something, an icon like this in the right side. So he will just say like here it is a roadblock, or don't come to this side. So he will just alert the before members getting into that. So inter-process communication is nothing but if a process faces a problem, so it will just communicate with the other process so that it will not commit the same mistake again and again. So for this reason, inter-process communication plays a major role in this operating system. And then memory management, as I had discussed it before, process scheduling also discussed it in this previous. And then handling interrupts. So interrupts, in this previous video we had discussed about the interrupts. Interrupts is nothing but some emergency tasks or high priority tasks. So handling those high prioritized works is a major thing in this hardware control, whereas communication with the machine plays a major role in this hardware control, because without the help of the machine we can't complete the task even if we have those device drivers. So communication with the machine is the most important thing. And then while coming to this system calls, so system call, read is a system call. So in this read system call, it has three types. I only mentioned three, there may be more than three, I don't know about it. So file descriptors, buffers, and then this is a value, something like n value. So here read is a system call which consists of these three constraints, file descriptors, buffer, cache, n. The user will not have a particular clarity regarding this read constraint. So the file descriptor is not known by the user, buffer is not known by the user. He will just directly give the value which is to be read into that particular file. So he will just give the file name or file path here, and the buffer will be filled directly with the help of the kernel. So the kernel plays a major role in executing every system call. So kernel will just decide the file descriptor, kernel will just give the buffer value, and then kernel receives the data from the user. So system call is nothing but a function call. Function call is in the case of kernel. So function call is in the case of kernel, system call is in the case of user interface, kernel interface. And then system call will be predefined in a library. So system calls will be predefined in a library. Kernel, with the help of kernel, it is known as a function call, whereas in the case of a user it is known as a system call, as I had said before in this second point. System calls helps us to access the kernel space operations in the program. So with the help of system calls we access the kernel space operations in the program. So with the help of this kernel space operations we will just complete the work which is need to be done in this operating system. And then if we just come into this file system, so file system, if we just consider here, so the file system will be like this, something like a tree, something just like a tree. So if you just consider here one main thing, user. So here it is a user. So user will just get into the kernel. So kernel will have different types of libraries or directories which are represented with the help of this slash symbol. So with the help of these directories, they will just access the files which were required for completing a particular process. So kernel have different types of file libraries. So it will just access the files in this file libraries and use it for the completion of the application. And now let us get back. So here we can just see a tree like structure. Here we had just discussed it in the paint. So it is in a tree like structure, right? So it contains the directories, and then directories contains files. So the structure of a file system. So the file system will have a boot block, super block, inode list, a data block. So we will just discuss one by one about these blocks. So first one, the boot block. So boot block is nothing but the code which is already created, already written code, predefined. We can't write the write or the read code in this kernel every time, right? So we will just save it as a file, executable code file. So we will just save it as a files. Every file has a boot block, that is predefined instructions. Boot is nothing but a predefined instruction. So if you just execute a system call, and in the kernel it will have a executable file which is regarding that particular system call. So they will just use that already predefined instruction, and then they will just complete the things which are required. So predefined instruction is a boot block. And then super block is nothing but it has a size of a file system, number of files it can store, and where to find the free space. So super block consists of all these details as the file size of the file system, number of files it can store, and where to find the free space. Inode list is nothing but the index node. It will have some index node. Every file have a unique inode. So index node, inode list is nothing but it will every process, every data structure. We discussed it in the previous video regarding this inode, right? So inode is nothing but the unique identity for every thing, every file or every data structure, whatever it may be. Unique inode, unique identity, unique number is an inode list. Inode list has a list of modes in a file system. Index node, every file have unique inode. Data block, it contains inode list and contains file data and administrative data. It consists of all the data which is required for completing a particular operation, all the inode list, and then file data, and then administrative data. So the internal representation of a files. In Unix, every file has a unique inode value. Process interacts with the file using a set of system calls. Inode exists as a static form, and kernel reads them into a main memory and modifies them. So inode values will be the in Unix, every file has a unique inode value, as I had said before. Process interacts with the files using a set of system calls. So if you just call a system call, then it will just get into the kernel and it will just access the files which were in that particular directory, and the inode exists as a static form, and kernel reads them into a main memory and modifies them. It will be in the secondary memory. Those inode values will be in the secondary memory, and it will just call into the main memory and then modifies them according to the use of particular application. According to the use of an application, inode exists as a static form, and kernel reads them into a main memory and modifies them. It consists of data, disk layout, file owner, access permission, access time. So it internal file, it consists of data like a disk layout, file owner, access permission, access times. These are the details which were consisting of these inode things. And then file data structures in the kernel. There are three types of data structures. They are user file descriptor tables, and then file tables, and then inode table. Inode table is nothing but the separate unique value tables, for particular process or particular data structures. So for each process there will be a file descriptor table. So each process will have a different file descriptor table. File descriptor table is nothing but it represents the state of a particular process. So it represents the state of a particular process with the help of a table. So file descriptor table consists of three signals, that is 0 standard input, 1 standard output, 2 standard error. File table is a global for all processes. Three tables maintain the state of a file. We will just discuss these things. File table is a global for all processes. So if you just consider the byte offset, byte offset is nothing but the adding of things, or we can just say like the file descriptors. This is a descriptor. So if you just add the initial value to this descriptor, then it will just show its increment. So increment of things is known as a byte offset. It is not much important. And then user file descriptor to file table. So from the user file descriptor, you will just pass some value, or you will just call a system call. If we just call a system call, then with the help of the kernel, it will just get into the file table, and in a file table it will just access a file which is in this file directory 3. So in the file directory 3, it will just search for the inode value of that particular file. After getting that particular inode value, it will just bring back again to the file table, and from user file descriptor, it will just execute the whole thing in the kernel. So all the details of the F3, it contains all the details of the F3, access rights and byte offsets. So this is all regarding the systems, subsystems, and then file systems, or architecture of a Unix operating system. Thank you.